Great. So I'll talk about implementing two pretty common machine learning methods, elastic nets and random forest. And I'll do so at a pretty basic level. There's a lot of theory behind these methods that one should know before trying to implement them. But I just want to share that implementing them is actually pretty easy. It's not so scary to do so. And then I'll mention a couple of reasons why you might want to do it. First, just if you want to predict things, these methods often outperform our sort of normal OLS regression methods. And this is particularly true of random forests, because it can capture complex interactions with your data that would be difficult to think about and then engineer specifically. OLS can struggle in the case where you don't have many more observations than you have predictions. This is not often, we try to not have that be the case in our academic work, but sometimes, data availability might make that the case for you. And so I've listed some reasons why OLS struggles when this is the case. I'm not going to go through them, but I think we all sort of have that intuition that you shouldn't do OLS regression if your observations, aren't sufficient for the number of predictors that you have in your model. These methods, these machine learning methods here, do help to resolve the issues with the N to P ratio problem. Another reason why you might care is just data. If you're interested in data science and data analytics jobs in the real world, these methods are recommended and usually required. So if you want to make that transition at some point, these are really useful techniques to have in your back pocket. And what I think is awesome recently is that there's some very cool academic work coming out lately in top journals in our field, the fields of social psychology and political psychology. So I've listed a few here that all use one of the two methods I used today, last nets and random forest. So let's set up a problem that we want to solve. I'm going to use data from the FIFA video game series, and we'll use in-game player statistics from the 2019 version of the game to try to predict how valuable a player would be on the open market. If we were to use the full data set of players, we'd have a lot of observations to predict from. So you predict with, you probably wouldn't see a difference between our normal OLS regression and elastic net regression, and then maybe only a modest boost in predictive success from OLS to random forest. So I'm going to make a situation where elastic nets and random forest might prove useful. So let's pretend you're a statistically inclined manager of a professional US soccer team, the Fayetteville Flops, and you want to build a predictive model of player market value. You can sign undervalued players and then sell them to larger clubs for a profit, making enough capital to become a club yourself. I don't know how soccer or football transactions work, and so soccer people out there, I'm really sorry for just butchering this, but let's pretend for today. You only have data from the last couple of years of US youth national teams because you know somebody who knows somebody who knows somebody. But just to say you don't have a lot of data, but yet you want to build a model that you can use successfully, for your purposes as this sort of lower, sort of semi-professional US team. The packages you need, there are a bunch of useful packages you can use. The first couple are just helper packages that aren't necessary for implementing these models. The real libraries you want, the real packages you want are Ferret, which has a lot of functions for streamlining the machine learning pipeline. DLMNet, which has useful functions for efficiently estimating penalized regression models. ElasticNet is a version of penalized regression. And then Ranger, which has awesome functions for implementing random forest models. There are other packages you could use, but these are the ones that I stick to because I find them useful. I've gone through a bunch of importing and processing steps that I'm not going to cover today, but I wanted to include just in case you're interested. These steps are necessary, of course, if we want to implement these types of models. So I'll skip a few of these pieces here. Well, we can take a quick look at our most valuable players in our data set. And so our most valuable player here is Christian Pulisic, who is valued on the open market at this point in time at about 1.8 million euros. spoiler alert, he's become a pretty successful player in the Premier League. I guess a little bit disappointing given how hyped he was, but it just goes to show the range of values in our data set. We're going to try to predict these values. He was valuable because he's skillful and he's young, and so we can kind of look at, how much do agent skill matter for how valuable you are, what other features matter, and then can we accurately predict the player's value. Again, more data processing steps just to make our data a little tidier and useful for these methods. We're not missing any data here, but I want to point out that you'll want to deal with missing data before implementing these techniques. Perhaps imputing values we're missing or removing variables where there's a lot of missing data. That's for another tutorial. We'll just take a quick look at how our data is distributed. Everything looks pretty fine, except for, of course, our value metric, as with most of these monetary metrics, is pretty skewed. So we'll just quickly transform that from being in its normal format to being the log of value. So our dependent variable will become player value in terms of the log euro value. And then we'll check out our two categorical variables here, which are fairly balanced, I guess. So enough about the data. The first thing you want to do is to split your data, not the first thing, but the next thing you want to do is to split your data into training and test sets. We're going to build our model on training data, attempting to balance bias, which is how well our model is predicting the actual values in the training sets, where low bias means we're capturing the data really well, you're fitting to the data really well. High bias means you're underfitting the model and making wrong predictions. We're going to balance that with variance, which is how much our parameter estimates would change if we trained on a different sample of data. So if our parameter estimates would change a lot from one set of data to the next, it means we're overfitting to our training set. And that's bad. So we're going to attempt to balance these two things, accuracy and not overfitting when we're training on our training set. Then we'll evaluate our model, and that's called a side test set. So I've written some code to do that here. We'll split 70% of our data into the training sets and the remaining 30% into our test sets. That's a pretty common ratio, but you can use others. You could also use validation sets. So you can split it into training, validation, and test if you want to even fine tune your model more on a validation set. That's common with more complex data sets and models than we're using today. We'll remove some variables we don't need. And then lastly, we'll center and scale our data. This is required by elastic net regression, but not by random forest, although it's fairly common to do this before most of these techniques. So we have caret as some pretty useful pre-processing function here that I've gone through, and then we'll apply this these pre-processing steps to both our training and our test data. Next, we'll just build our standard OLS regression model function. We're using the LM function, which I'm sure all of you have used before. We can look at all of our predictors and their relationship to player value. And I'm not going to go through any of the particular features, but I will note that not many of them are significantly related to our outcome player value. And that's potentially because when you have so many predictors, there's a high chance of multicollinearity between your predictors, which OLS struggles with. Another problem when you have with OLS regression, when you don't have many more observations than predictors, is that your regression coefficient standard errors are inflated. Of course, leading to reduced opportunity for significant relationships to emerge in your model. We are doing a pretty good job at predicting player value with R-squared value of 0.876. Our model seems to be well fit to the data, but maybe it's actually overfit to the data, given all the problems that I've outlined before. We can sort of look at our coefficients visually using plots that Diego and Ani covered really nicely earlier. and see like the uncertainty around our different regression coefficients is pretty high. Next, we'll take the model based on just the training set and make predictions on the test set. That's what I do right here. And we're going to compute two performance metrics, RMSE and R squared, comparing our predicted values to the actual player values in the test set. Lastly, let's see how our model performed. And our model is still decent in explaining about 68% of the variance in player value in our test set. But this is a fairly big drop from how well we were predicting values in the training set. To me, this suggests we overfit our model. And now we're not generalizing as well to new data. Again, an issue with OLS regression when our sample size is not much larger than our predictor. So finally, let's get to these other techniques and see how they perform in relation. First, we'll implement an elastic net model. It's a form of penalized or regularized regression. What that means is that we're going to add a penalty term that will shrink coefficients that get too large. So if a regression coefficient gets large enough, we'll add a penalty that reduces that value, because overly large coefficients are indicators of overfitting. And these are just kind of similar to how you get inflated effect sizes in small sample studies that are then that aren't reproducible later. This reduces model variance, weakening our likelihood of overfitting, allowing for better model generalization. Of course, the model won't be quite as accurate on the training set, but our goal is to balance accuracy on the training set with accuracy on other data, on other samples. ElasticNet is a hybrid of two other techniques. I'm not going to go into these other techniques for ridge lasso regression here, other than to say they have different penalty terms. We're going to use what's called repeated k-fold cross-validation to find the best parameters for our model. I don't plan to dive into that, but we're basically going to just take our training set and we're going to iteratively train on different combinations of samples within our training set, then average across all of the iterations to estimate how well a model with a given set of parameters is performing. I'd encourage you to look up cross-validation if you're interested in implementing one of these techniques. It's a really important concept. And we're going to try to optimize two parameters for elastic regression. First is alpha, which controls how ridge-like or lasso-like the model is. And the second is lambda, which controls how much large coefficients are penalized. And we'll use 10-fold cross-validation repeated 5 times. So this is an example of a function we're going to use caret train function. And here's an example of one way in which we can train our model. I've specified different parameters for different values for our two parameters, alpha and lambda, that we're going to try out and see which one best fits the training data. After the training, we'll see which model or which set of parameters was best fit the training data while also penalizing large coefficients. And we end up with an alpha of 0, which is fully ridge-like, and a lambda of 0.01. So the nice thing about elastic net regression is that in addition to it better generalizing to test samples when we have this issue of not many observations relative to predictors, we can interpret our regression coefficients just like we did with OLS regression. And so we'll get regression coefficients just like we did before. So, reaction, how well you react to situations on the field positively impacts player value. Interestingly, being a striker lessens your value relative to being a defensive back. I don't know much about soccer, so I can't say why that might be, but that's the case. We can also get what are called variable importance metrics, which describes how much a model relies on a given variable to make predictions. And so reactions, how well you react to situations, how well you can strike the ball while it's in the air, how composed you are, all really matter for how valuable you are. And then again, we can see how well our model generalizes to the test data. So we'll make some predictions using our training model to make predictions on the test set and then compute our two metrics. of model fit or accuracy. And what we see is that we have an increase from 0.6 in the OLS, 0.68 in the OLS case to an R squared of 0.748 here with our elastic genetic model. So we see a fairly robust increase in predictive performance by using a model that regularizes, that includes regularization steps. Again, this is likely because we don't have a lot of data. We have a lot of predictors that might matter, and OLS tends to struggle, whereas this technique, elastic net regression, helps with that problem. Next, I'll talk about random forest modeling, which are extremely popular these days. Random forests are an ensemble method where you construct a lot of individual decision trees. Then, kind of like wisdom of the crowds, you take the predictions of all of these individual trees, average across their predictions, and then by averaging across the predictions of lots of different trees, you end up with really successful single predictions. And then an individual tree is what it sounds like. It's like a series of decision points or splits on your predictor variables that attempt to maximize your prediction of whatever outcome. And there's so much more to decision trees and random forests that make them interesting and useful, but I don't have time to cover them. So we'll move forward, but I'd encourage you to read more about it if you're interested. Like with our elastic net model, we'll use repeated cross-validation to identify the best tree structure. And then there are different parameters for random forests that we'll want to specify. Things like how many predictors we use for each tree. We're not going to use all of our predictors in each individual tree. We're going to use a subset. We'll also specify the number of trees to grow within our forest, and we'll try 500, although you could pick more or fewer depending on your constraints. We'll specify a minimum node size, which controls how deep our trees go. And then we'll choose a split rule, which just determines how to best split a predictor variable in terms of the outcome. Do we want to split composure at a score of 80 out of 100 or 70 out of 100 or so forth? Your split rule helps determine what value of the predictor you split on to try to make a prediction. So we're going to train our model also in Caret, and that's kind of why I like Caret. You could use one package to streamline your training approach. I've specified all of the different parameters and specified that we're going to use repeated cross-validation 10 times, repeated tenfold cross-validation repeated 5 times. We'll look at our best model, so what parameters maximize our fit on the training data. And it's according to our training results, trees with 10 predictors each using the variance split rule and a minimum node set of 3 maximize fit to the training data. You can actually visualize all of the parameter combinations in terms of their fit. We could have done this with our elastic net model, but I didn't like the way it looks, so I didn't show you. But here we can see, the best. This is I plotted each parameter combination in terms of the R squared on the training data, and the one that maximized R squared on the training data was this one here. 10 predictors, randomly selected, minimum node size of 3, the variance splitting. So the downside of random forests is we can't obtain or interpret individual regression coefficients. We're averaging across the ultimate prediction. We're getting our ultimate predictions by averaging across a lot of individual predictions by many individual trees with many different splits on different predictors across different trees. But we can get the same invariable importance metric like we did for elastic net model, telling us what variables our trees and therefore a random forest relies on to make predictions. And it suggests that skill with dribbling the ball, reactions to different situations of the field, and composure really matter for how valuable you are as a player. Like before, we can get some predictions on our test data using our trained model to make predictions for the players that have been held out. We can compute our two accuracy metrics, and we can see a bigger jump in performance this time, all the way up to 0.85, explaining about 85% of the variance in our player data, up from both the elastic net model and OLS regression. So random forests are really good for prediction at the cost of a little bit of interpretability, whereas elastic net modeling is kind of like a middle ground in terms of prediction, while still allowing the same interpretation of OLS coefficients like you are used to with OLS regression. And so that's it for today. Hope that was helpful for everyone.